Gentlemen, welcome to the international webinar on causal interference using machine learning and deep learning, organized by IASTM in association with IRAJ Webinars. On the behalf of entire organizing committee, I'm Isaac Pereira, organizing secretary. Would like to welcome you all for this webinar. Ladies and gentlemen, let me introduce our organization. The motto behind this non-profit association is to bridge the gap between students, professors, academics, and industries from multidiscipline. Apart from organizing various seminars, expert talks, and conferences, we have various highly rated multidisciplinary journals in the field of science, engineering, technology, and management. Since our inception, we have been arranged various international conferences at various parts of the world, like New York, London, Australia, Hong Kong, Dubai, Bangkok, Kuala Lumpur, India, etc. More than 1 lakh people across the globe are associated with us, and more than 5 lakhs research papers have been presented and published during our journey. Today, I'm glad to welcome you all as a member of this fastest growing network for the advancement of science and technology in terms of research and innovation. Today, we are very much fortunate to have an eminent professor, an expert who is joining this webinar as an expert speaker and guest. His name is Dr. Abhimanyu Mukherjee. Presently, he's working as a research economist at Amazon, Sunnyvale, California. Now, I'd like to welcome our Professor Dr. Abhimanyu Mukherjee to deliver the webinar.
Okay, thank you very much for being here, and thank you for having me. As was mentioned, the topic of today's discussion is going to be on causal inference using machine learning and deep learning. And I think a lot of people on the call might already be familiar with machine learning and deep learning, but causal inference might be a little bit new. So I will spend a little bit of time giving some background on that problem space, and then we'll move into how specifically machine learning and deep learning can kind of help solve those problems. So to give some quick background on myself, I work as an economist at Amazon in the United States, and my background is primarily in causal inference, and I use machine learning methods in my research and in my work. So I'll take some inspiration from that when sort of giving examples and when explaining things here. So as I think most people would be familiar, machine learning focuses usually on a problem of prediction. So generally, the idea in a standard prediction problem of this nature is that you want to guess what y is given some x. And so the idea is that x may be something that is in a panel format, it may be cross-sectional data, it may be time series data. But generally, the goal is that there is some target variable of interest, let's call it y, and that is what you're trying to use all the information that you have available to try to predict. And usually you can test accuracy in such cases against some measure of ground truth. So what I mean by this is there will usually be some real y values, and you can test different methods and see which one is doing the best job of predicting successfully the y value that you're interested in. And so causal inference asks a slightly different question. So here we're kind of thinking not just about can you use x to get a good prediction of y, it's instead looking at what actually happens to y when we think about changing the value of x. So this is a slightly different set of problems because here usually x is a variable that we can control or influence in some way. And the idea is that we want to find out when we were to change this x value at different points in its distribution, what would actually happen to y for each of those points. And an important thing to remember is that if x causes y, then x will certainly be a good input that will help predict y, but the other way around is not true. So you can have x predicting y, but x not causing y. And I'll give some examples of why this might be the case. And so because of the nature of this problem, it can be very difficult to validate solutions for causal inference. So understanding whether or not x is the cause of y is not an easy thing to do. And the different techniques, the different approaches that are typically used for this kind of thing, they all require assumptions, and not all these assumptions are testable. So unlike standard machine learning problems where you can kind of compare different models based on predictive accuracy or some such measure, in causal inference, you usually are limited to out-of-sample testing or testing the assumptions of the method that is being used. And so that makes it a very challenging problem space for researchers to kind of validate their solutions. And I will talk a little bit at the end about ways in which we can think about validating causal inference applications specifically. So as I mentioned, when x predicts y, it does not mean that x has caused y, and it will not give you information on how y will change if we were to change x. So you can imagine, for example, that if you were using x to predict y, there may be points in the distribution where a small change in x has a small change in y, but there may be points where it is more sensitive. So a small change in x can actually cause a very large change in y. And so because predictive models usually are not giving you this kind of information, it may not help you decide what X to choose. So for example, I may want to choose the X which has the maximal impact on my Y, and prediction can help you get to a point, but it will not, for example, be able to tell you whether a larger change in X will have a larger impact on Y or not. That'll require some assumption, either the predictive model itself is causal or some additional distributional assumptions, which is kind of what we will usually be thinking about in causal inference. And guessing why, which is the problem of prediction, may not be enough. Sometimes there is a very important case to try to understand why X predicts Y. And so to give you an example of this, like if you were to test the efficiency of a new drug, sometimes it's not sufficient to know that a drug is effective. Sometimes you want to be thinking about what is the specific channel through which it is acting, and that might give you information on new drugs to develop, for example. Um, and so choosing X can be a difficult problem, but it is usually more useful for decision makers or businesses. So from the business perspective, like one quick example here, like let's say the goal of a business is to sell as much product as it possibly can. Let's say someone is selling phones. They want to sell as many phones as they possibly can. And the decision being made is what is the best price. And so understanding that price will have a negative association with the quantity sold, that is a kind of a prediction framework, which is not very useful. What the decision maker really wants to understand is how can they maximize their revenue? So what is the best price they can set? And also if they were to change the price, how much impact are they actually having on the Y variable, which is the quantity sold of interest? So I'm making a clear distinction here between a problem of prediction and a problem of causation. And you might be asking yourself the question as to whether this distinction really matters, like how important is it really? And so to give you an example to sort of solidify the reasoning here, what I've plotted over here is total arcade revenue in the US versus CS doctorates that are awarded. And as you can see very quickly from this chart, these two date time series are very strongly correlated, the 98.5% correlated. And so what this means is I can just, if I was to, if let's say I was interested in predicting CS doctorates based on total arcade revenue, a very simple model would be able to predict it very well, and vice versa. If I was to say I want to predict arcade revenue based on CS doctorates, based on this trend alone, either variable can be used to predict the other. But as you can think of intuitively, building more arcades will not lead to more computer science doctorates, and just subsidizing doctorates may not lead to more arcade revenue. So here, a predictive model will not actually give you much insight into what is driving this trend that we're seeing here. And so predictive models in general are not prescriptive. They're not going to be able to do a good job of telling you what you should do. So here, if I had to try to explain why am I seeing this trend if neither of the variables is causing the other, you can think maybe there was some underlying economic reason why this is happening. So the computer revolution, information technology boom, that could explain why more people are studying computer science and staying into PhDs in computer science. And it could also explain why maybe people are more interested in attending arcades and therefore arcade revenue goes up. So in an example like this, there is an underlying cause, and some logical reasoning can kind of lead you to what is that underlying cause. But in general, just looking at a time series trend like this is not going to give you a sense of what causes what. And to make things even more interesting, there may be cases where you have patterns in data that you cannot explain. There is no real logical explanation or an underlying cause that could be addressing both of them. So if you look at this chart here, like what it's plotting is divorce rates in the state of Maine in the US versus the amount of margarine consumed in the state of Maine. This is average margarine consumed per household. And once again, you can see that these time trends are very strongly correlated. So either variable would predict the other. But explaining why margarine consumption predicts divorce rates or why divorce rates predict margarine consumption, that there is no good underlying explanation for this. And so causal inference frequently deals with situations like this, where it can be quite challenging to understand what actually is causing something to happen. And I'm sure others would have seen such patterns in data where there is no clear explanation. So this is kind of the kinds of problems that we're interested in, but it's very important to understand what is actually leading to the trends that we're observing. So coming more specifically to business problems of causal inference, which is kind of the focus of my work, what I'm gonna kind of do here is just give a few problem statements, and you can think about like when certain problems are very easily mapped to prediction problems and when there may be something deeper going on. So whether or not you should be using causal inference depends on the kind of problem that we're trying to solve. So let's look at the first one, like what product should I recommend to a user? This is a pretty simple problem of prediction. You can kind of see what the user's behavior has been, what kind of things they have bought. And accordingly, you can think about, okay, what would be the best thing to predict their future purchases? And therefore, that is what you should be recommending. A second one is a more specific case. If a customer buys a phone today, how likely are they to buy a phone case? Again, this is a problem of prediction. You can regress phone case purchases conditional on past phone purchases, and that'll give you kind of information. Now, the next three are more in the realm of causal inference. So one important one, would a blue color theme page drive more purchases? So this is actually a famous problem that Microsoft had dealt with at one point. And it turns out that just changing the color theme of a web page can really, really influence the tendency of people to spend time on that website and to engage with it. And this is clearly a problem of causal inference. Like before you have any data on how people would behave with a blue color theme, there's no real way for you to predict what that behavior would be. And so this is kind of where experimentation, causal inference comes in, and it's a good kind of example of a very high impact problem that requires causal inference techniques to solve. And the last two are dealing with kind of marketing discounts. So one is saying, should you offer a $10 discount on subscriptions to your product? And the final one is, are Black Friday sales promotions worth it? So both of these are problems of causal inference. You're making a change to some feature that you can control. In this case, it is the price. And the idea is saying, like, should you be thinking about cutting your price? How do you know it's a good idea? How do you know that's actually going to help your business in the long run? And these are the kinds of problems that causal inference is more suited to answering. So I'm going to focus on a very specific case here to try to give like some background, and then I can go into some detail on the different methods that we can use, in particular how machine learning and deep learning methods can come in to help answer this question. So let's focus on this one general problem structure where you have two customers. So you have a customer A and a customer B. And let's say that these are customers in a business, and the business is thinking about running a marketing campaign. And this marketing campaign, let's think of it as being something that you can't easily control who has seen the marketing campaign. So it might be like a television ad or a radio ad or something like that. So people, you can't really tell for sure who is going to see your ad in advance or who is going to be exposed to your marketing campaign in advance. But you do observe which customers are actually exposed to it. So for this case, let's say that customer A does not see the campaign. And then after not seeing the campaign in row number one, they have some revenue A that they spend in the future in the company, let's say over the next 2 weeks. And similarly, let's say there's a customer B who gets exposed to the marketing campaign, and they have some revenue B that they spend in the future as well. And the question that you're kind of trying to understand here is whether this marketing campaign was a good idea. So the question, to phrase it more precisely, did this campaign generate extra revenue for the company? And so this can be a very important problem for businesses because marketing, advertising expenditure is usually pretty expensive. So it's important for the business to try to understand, was this investment worth it? So this is a simple matter of valuation. You're trying to understand, like, is the return on the investment that you're making positive? And if so, you might want to think about it being something you do going forward. So do you want to use this campaign to try to give you information that helps you run better campaigns going forward? And another very interesting question would be, can you do a better job of targeting campaigns in the future? So let's say that there is a big website retailer who is running this experiment. They're trying to run a marketing campaign. And let's say that it's more effective on certain types of people. Let's say that younger people are more interested in the campaign and they tend to buy more after being exposed to the campaign, but older people are less interested. So now the best way to optimize your spending would actually be to focus the marketing towards these younger people and not spend so much on exposing older people to it. But this is something you can't know in advance. You have to kind of analyze your data to understand whether these patterns are there and how you can target better in the future. So coming back to the problem, like what we observe here is a customer A who has not seen a campaign and a customer B who has seen the campaign. And from this, you're trying to understand what is the value of the campaign. So although this is what we observe, this may not be the best thing for us to observe. So to answer the question, what would actually be more useful is if you could see customer B in two realities. In one reality, they have not been exposed to the campaign, and in another reality, they have been exposed to the campaign. So in row A, in the first row, we basically see a revenue, which is their revenue have they not seen the campaign. And in the second row, we see revenue if they had been exposed to the campaign. And very logically, very intuitively, if you were to take the difference between the revenue in the second row and the revenue in the first row, the only thing that's really different is that in one situation, there has been exposure to a marketing campaign, and in the other situation, there was not. So for that exact same customer, if you could see both of these things, you can just take a difference of their value of their revenue in both scenarios, and that will give you a sense of how valuable was the marketing campaign for this particular customer B. And if you were able to see this across all of your customers, then the total value of the marketing campaign is just the sum of the difference in their revenue between these two states of the world. But the problem becomes that you don't actually see this. So you're missing some data. In an ideal world, what you would like to see is you would like to be able to see for each customer how exactly would they have behaved with and without the marketing campaign. But you can only see one of the two realities. Either the customer has seen the marketing campaign, in which case you can see their marketing, you can see what they spend after seeing a marketing campaign. Or you have a customer who has not seen the marketing campaign, and you can see how they would have behaved, what they would have spent had they not seen the marketing campaign. So these two conditional things of the same customer with and without the marketing campaign, these in causal inference terminology are called potential outcomes. And the problem of causal inference really comes down to one of missing data. And the missing data that you're not seeing here is if you see one potential outcome, for example, which is when the customer has seen the marketing campaign, that by definition means they could also not have simultaneously not seen the campaign. So you can only see one of the two rows, you cannot see both. And so causal inference comes down really to a problem of missing data. And so missing data, by framing the problem as one of missing data, it's actually helpful because machine learning can help in this problem of missing data. So before I go any further with the missing data track, I wanted to spend a minute here to talk about some other ways to solve this problem. So missing data, the methods that machine learning and deep learning really help with in causal inference is that the missing data can be guessed, can be interpolated. And once you have the missing data, now you have all the ingredients that you need to sort of estimate your causal effect. But there are other strategies such as RCTs, which are randomized control trials or online experiments for A/B testing. There's many different settings. So RCTs can basically avoid this problem by getting you an average effect, which does not actually require you to estimate the counterfactual, the unobserved data for every single customer. But experiments like RCTs are not always possible. There may be cost structure issues. For example, for a company to run an experiment on all of its customers can get very expensive. Another one has to do with ethics. So if, for example, the marketing campaign involves some kind of promotion, such as a Black Friday deal in the US, where there are some products that are being offered at a discount. You cannot offer that discount to some customers and not offer it to other customers, because if they find out about it, your customers will be very unhappy, and that'll ultimately hurt the business. And it's also an unethical thing to do. Another one has to do with scaling. So let's say you're able to run an experiment on a small group of a few hundred customers. So in that experiment, you would expose some of those customers at random to a marketing campaign, and some of them you will not. And then you can kind of compare them, right? But it may not be possible for you to control exactly who is seeing what, who is being exposed to the marketing campaign. And it may not be possible for you to scale this to a big enough customer sample to actually measure an effect. So all of these become challenging. So sometimes you're pretty much stuck with only the data that you have collected. You cannot be running any experiments. You cannot be running any interventions. And so this class of problems has to do with observational causal models, which is usually what businesses and technology companies have to deal with. And so it's a more general problem statement, and the solutions that we think about are more broadly applicable. And so the idea generally is you want to think about how do you predict the missing data. So if you have seen a customer B who has been exposed to a marketing campaign, and you can see how much money they spent after the campaign, you can think about, okay, can I predict how this customer would have behaved if they had not been exposed to my marketing campaign? And so the idea is you use all available information to try to guess this missing feature of interest. And machine learning is very good at kind of doing this guesswork of predicting the missing data. And so that's where machine learning approaches can be quite useful. So what I'll do now is kind of give a quick overview of a few techniques, which are like there's many methods you can use, but broadly they can be classified into a few logical categories. And I'm going to spend a little bit of time on each of these categories to build some intuition for why they work and how you might be able to apply them. So the first one has to do with matching and clustering. So if you look at the diagram below, let's say that you were able to group your customers together. So suppose you see that historically, based on the information you have collected on your customers' click patterns and what they've bought and how often they've been on your website, you might be able to say that customer A, B, C, and D, they tend to behave in a very similar way. So customer A buys maybe on average a t-shirt once a month, and customer D will also do the same thing. And so if you can kind of think of these customers as representing each other. So customer A and customer D are so similar that maybe you can think of them as being interchangeable. And what this means is now if you think of this group of customers and in the future you run a marketing campaign that only customer B has been exposed to, you know that historically A, B, C, and D have all been behaving very similarly. And now customer B has had something change in their exposure to the marketing campaign, but A, C, and D have not had that change. So what you can do is you can observe customers A, C, and D, and you can say, okay, how have they behaved? Because these guys have not been exposed to my marketing campaign. And they can be used to represent or make a guess of how customer B would have been behaving if he had not seen the marketing campaign. And so essentially, this problem comes down to an intelligent way to group customers or to group units together such that you can say that these are so similar that if I know some of their behavior, I can make a guess about the behavior of the person that I'm not able to see. And in this case, it'll be customer B's behavior without marketing that you're not being able to observe. Um, and so other customers in B's cluster or group can represent B without the marketing campaign. So for those with familiarity with machine learning methods, propensity score matching or weighting or quotient exact matching, these are explicit matching methods. So they'll kind of tell you based on the different observable variables that you have, how similar any two customers are. And so you can think of using supervised methods like this to group customers together. And it doesn't have to be supervised. Like sometimes you may not even care why the customers are similar. It only matters that you know that they are similar. So you can think of using k-means or hierarchical clustering. So these are unsupervised learning methods. And from that also you can achieve something very similar, which is ultimately you can think of groups of customers that will behave in a similar way. And grouping can become a little difficult when you don't have too many customers. So suppose you had only 50 customers, you're a very small business. It may not actually be possible to find a sensible grouping of customers such that you can say that, oh, A, B, and C, and D are all very similar all the time. So an alternate way to do this is to think about creating a fake customer. Think of a synthetic customer that you have constructed, which will be a proxy or a representation of B had they not seen the marketing campaign. And so the way this strategy works is you will be taking your actual customers and you will construct a weighted average of these customers using some kind of flexible regression model. And you can do this by training on historical features. So suppose I look at the features of customer B and I regress them on the features of customers A, C, and D. What that will do, simple linear regression, for example, the coefficients can be interpreted as weights, and you're kind of saying that I can now weight A, C, and D together to create a new version of a customer that is an estimation of how B will behave. And so customer B without the campaign can be estimated using historical data because you have all the information needed to think about B's behavior in the future. And now if you see that B, the real customer B, has behaved differently from the synthetic estimated customer B, the reason for that would most likely be the marketing campaign, because that is the major change in customer B's exposure that you have not accounted for in your model. So comparing the synthetic customer B to the real customer B who was exposed to the campaign, that would be a very good way to kind of think about, okay, if I look at my predicted behavior of B as per the synthetic control versus the actual customer B's behavior, the difference between those two is a good proxy for the value of the marketing campaign to be. And you can think about doing this for every single one of your customers. And then you can actually estimate for each customer how much was their behavior actually impacted by the marketing campaign. And I wanted to stress this a little bit because it gets back to also the point I was making about sometimes this can be used to select what customers you should be focusing on. So in terms of where to prioritize your marketing spend or where to focus your advertising expenditure. Methods like this can give you some indication of what customers are most impacted by a marketing campaign. And the most impacted customers are going to be the ones that give the business the highest rate of return on that investment. So you can think about focusing the investment in that direction. So previously, like the methods around clustering, synthetic controls, like what they're doing over there is you're using actual customer data to create a grouping or a fake customer that can stand in as a proxy for the customer's behavior that you are interested in observing. Another way to do it is in the general family of methods called meta learners. And what this does is it uses all available features to train a model to predict customer revenue. So I will use my historical data for all the customers that I have, and I will not worry too much about are these people seeing the marketing campaign in the future or not. So all I'm doing over here is I'm taking all my available features and I'm using them to train a model to predict customer revenue. So you can think of some features as being how often does the customer log on in a day, what is their average spending in a month. You can think of how often do they buy products in a particular group. All of these things are things that will predict the revenue overall. And you also might want to think about customer specific features like their location, for example, like what city are they from, how old are they. Information like that can also be used to predict revenue. And so the idea is you spend a lot of effort training a very good model such that you can get very accurate predictions. So if you can achieve like a 95% or a 90% accuracy in predicting customer revenue, then this model is going to be useful for this method. So the idea is that if I can predict revenue very, very effectively, then deviations from predicted revenue can be attributed to new information that my model does not have. So for example, if I ran a marketing campaign such as this setting here, the marketing campaign is new information that is not going into my model. So any deviation from the prediction of the model can be attributed to this new information, to the marketing campaign. And so now coming back to the problem of customer B, if my model is saying that customer B in the next 2 weeks is supposed to be spending $10, instead I see customer B has spent $15. So now my model, if I know that my model is very reliable, I know that the customer B would very likely have spent $10 if he had not been exposed to something new, to the marketing campaign. So now here the value of the marketing campaign for customer B is the difference between 15 and 10. So $5 is the value of the campaign to B. And the advantage of like methods like this is that they are very flexible. Like I said over here that we need a regression model of some kind to predict customer revenue, but it really doesn't matter like what information goes into the model. It doesn't matter if it's deep learning, machine learning, nonlinear, supervised, unsupervised learning. It can be fully non-parametric. It doesn't really matter very much. The simple goal here is you want to have a model that can very, very accurately predict your customer's revenue, and that it can do this across different times. It should not be sensitive to seasonality or specific customers or anything like that. So if you can achieve a model like this, which is sometimes possible if you have a big enough sample set of data for your customers, then you can kind of use these methods to understand the effects of deviations from your model, which is when you make an intervention such as a marketing campaign or a sales promotion or a change to your website, whatever it is. Um, so on the same theme of kind of grouping and clustering, I think most people here would be familiar with random trees and random forests. And so there's a version of this called causal trees and forests. And they're similar to random forests, but the idea is that the optimization function is modified a little bit. So the exact technicality of how it's modified is a little bit complicated, so I won't be able to go into it here in depth. But to build some intuition, generally in a random tree or a random forest, what is happening is that at each node in the tree, you're splitting your sample based on some criteria. And so once you've kind of split the sample on many criteria across many, many levels of the tree, by the time you get to the leaf node, the final node, what actually happens is that the observations that are in any one node, they tend to be very similar to each other. So in leaf node number 1, all the observations you have there will be quite similar to each other. And in leaf node number 9, for example, again, those observations will be very similar to each other. So you can imagine that if I was to train such a model on my customers, the customers who end up at each leaf node, they will be very similar to each other, and therefore they will be very comparable to each other. So this is kind of like effectively getting you quite close to a clustering effect. And so leaf nodes will produce groups that are similar. And one of the additional pieces that goes into the optimization function is to try to make sure that you can identify leaf nodes where the expected causal effect is quite large. And this can also be used to help you target. So you can identify inputs you can identify the input features that are important in isolating causal effects. And so once you've done that, once you know which features are important in grouping, now you can you don't even need to use the tree anymore. Now you can go and put it into a different kind of model. And this framework is also useful in terms of heterogeneous effects. And so what I mean by this is that customers in leaf node 1 and leaf node number 10, they may be very different from each other. And so therefore their response to the marketing campaign could also be quite different. And so this is exactly what we were talking about when we said how best to target a marketing campaign, how best to target advertising expenditure. So you can sort of use methods like this to identify differences or heterogeneity in the treatment effects of your marketing campaign. And so this can help you identify which customers are most likely to have to be very impacted. And accordingly, you can sort of focus on how best to target your spending in that manner. So while machine learning methods can sort of be an alternate solution, the problem of causal inference is very old. So like this goes back to the 1960s, 1970s. People have been thinking about problems like this. And so this is, and like I think one very common area where people are familiar with this is when you think about experiments in the sciences, or experiments when testing new drugs or new medicines. There you have to basically understand what is the causal effect of a drug. So for example, like if you're looking at a drug for malaria, you want to understand how effective is this drug in treating the disease, right? And so the way like an organization like the Federal Drug Administration in the US would do it they would run randomized experiments. So they would say randomized control trials where certain people are exposed to the drug and certain people are not. And that method can allow you to sort of understand how effective that drug was. So the methods like this are very, very old. So they've been around since before machine learning really became mainstream technology, and before these methods became scalable enough for you to use it. And so another example is difference in differences, instrumental variables. So I won't go into much depth on these methods, but they're very traditional methods that have been used in the social sciences for many, many years. And machine learning does not necessarily just have to replace them. Like all the methods I talked about earlier, they're kind of targeting from the perspective of, let's say the existing methods are not good, what can machine learning do to replace them? But the point I'm trying to make here is that machine learning is not useful only in replacing these methods. Sometimes they can work together in conjunction with them to try to improve them, to try to give better results. Um, and so one simple example of this is in non-parametric model fit. So a lot of traditional methods in economics, they use linear regression or linear methods to sort of estimate some of the traditional methods. But that doesn't need to be the case. Those models do not necessarily require a linear fit. So you can think of non-parametric deep learning based methods that can do a good job as well. Another one has to do with feature selection and interactions. So let's say the FDA was running a drug trial. They need to think about, okay, what are the important features we want to think about such that everything is randomized effectively across the sample. And so machine learning, deep learning methods can kind of give you a sense, for example, what are the important characteristics of a particular patient that predicts how severe malaria is or what their probability of recovering from malaria is. And so really you want to make sure that among the people who get the drug and the people who don't get the drug, there is a good balance across these important features that predict the progression of the disease. And so that first step, understanding what those important features are, that is really something where something like a random forest method can add a lot of value. It can really tell you what is important in your randomization strategy. And another important one, which comes up in my work a lot, so I wanted to spend a little bit of time on that. It has to do with measuring long-term effects. So in the example that I gave around malaria, right? Let's say we have identified that in the next 3 weeks, taking the drug increases the probability of recovery by 30%, right? But maybe you're not just interested in the next 3 weeks. Maybe you're interested in the next 3 months. You want to understand like what are the like does it have long-term benefits? Does it reduce long-term impact? Does it reduce propensity to get malaria again in the future? And so understanding these long-term effects is another case where it may not always be possible to track these exact same customers. So having a machine learning model that can use the short-term inputs to predict the long-term effects, that can also be very, very valuable. And to spend a little bit of time on the business context here as well. So let's say you have spent some money on advertising or you have spent some money running a marketing campaign. You usually are only tracking your customers for a few weeks after that marketing campaign. You're not tracking them for years into the future. But sometimes the effects that you have can be very, very persistent. So if I see a very high impact ad that leads me to make a purchase, that might change my experience on the website completely. It might change my experience with the company completely. And now going forward in the future, I will always be spending more money. So really that one marketing campaign has had an impact on the customer, not just for the next few weeks or the next few months, but for the next few years. But this is something that's very, very difficult to keep track of. And it's very, very difficult to say that the campaign specifically was what led to that effect, because many things are changing over time. Many things change as you wait longer and longer. Um, and so finding an intelligent, well-disciplined statistical method to measure these long-term effects, that becomes very, very useful. And so the strategy to do this, it's in a family of models in econometrics called surrogate methods. And so, as I was saying, traditional methods usually only allow you for a short-term effect measurement. But what surrogate models will do is that they will quantify the relationship between the short-term observed outcomes, which, for example, will be the revenue or the propensity of recovery over the next few weeks. These surrogates are used in a model to predict the long-term outcomes of interest. And the long-term outcomes of interest here will be, for example, the total spending on different products 3 years into the future, or the reduced propensity of getting malaria a decade into the future, things like that. And so causal effects on surrogates can kind of be used to proxy for and estimate the long-term effects. So the diagram here kind of illustrates the high-level structure of a model like this. So coming back to the marketing campaign, you have a marketing campaign. It causes some lifts on the surrogates in the short term. By lift, I basically mean something has increased in value. So for example, in the next 2 weeks, maybe the spending for that customer is increased by $5 or $10. That is a short-term lift. And I can collect these lifts across all of the customers. I can collect their exposure to the campaign. Were they treated? Were they not treated with this marketing campaign? And I can also collect historical information about them, about their past spending patterns. All of that goes into a model that predicts long-term outcomes. And now the reason this is very important is because once you have a good model that can translate short-term effects into long-term effects, now you no longer need to worry about tracking customers. You don't need to worry about running long-term campaigns. You don't need to worry about any of that. All you need to do is you need to run something for a short term, which usually means it's a lot cheaper, less expensive to run. And once you run that marketing campaign or whatever it is for a few weeks, you can collect all of that information, put it in your model, and the model will tell you what the long-term value is going to be. And once you have that information today, well in advance of the actual value happening, it can allow you to optimize your investment. So for example, if you know that the marketing campaign was very, very effective and it's expected to have a lot of impact over the next 5 years, maybe what this means is that you don't need to run too many more marketing campaigns because you've already had a lot of impact. So now maybe you can avoid spending that money. Alternatively, it might reveal to you that it was very, very inefficiently spent. It did not have the impact that you wanted. And so now you can think about, okay, how else can I optimize my business? So it can lead you to a healthier strategy for your long-term growth, for your long-term business prospects. The last topic I wanted to touch on, I'll try to wrap this up in a few minutes in case anyone has questions and we still have some time for that. The last topic I wanted to touch on has to do with validating causal models. So coming back to the problem of machine learning and causal inference. So prediction problems in machine learning will generally give you some source of ground truth. Usually you can actually observe the outcome of interest that you're trying to predict. And so a model that is very, very close to the actual outcome is going to be a better model than one that is very, very far away in terms of its predictions. Causal models don't have any source of ground truth. So what I mean by that is, let's say I'm testing a new malaria drug. Until I actually run a trial where patients are being given this drug, I have no idea how effective it is. Maybe I have some logical explanations or some scientific reasoning that tells me that it should be effective, but I cannot say for sure. And in particular, if I have drug A and drug B, I cannot tell you which of them is going to be better without actually running through the experiment. And running through the experiment can be quite costly. And let's say you test drug A and you find that it is effective. There may have been a mistake made in the randomization. Maybe you selected customers who were very healthy, who received the drug, and the people who did not get the drug were all inherently a little bit less healthy. And now that causal effect is not measured properly, but there's no way for you to know that. There's no way for you to know that the 10% decrease in disease probability is in fact the actual value. So there's no source of ground truth for you. So kind of verifying and validating the reliability and robustness of your model can be a very challenging problem. And so I'll just quickly touch upon some general strategies to do this. So one important one is testing assumptions. So people who come from a machine learning background generally think of these things as black box. You kind of like throw all your inputs, throw all your features in there, and you just go with whatever does the best prediction. You're not really thinking too much about the assumptions that the model is making. And this is something that's very different in causal inference. In causal inference problems, you really, really need to worry about what are the assumptions you're making, how can you test them. So coming back to this example of a malaria drug, right? Like one simple assumption you're making is that when you do a random control trial, it has to be true randomization. And true randomization has certain implications. So one implication, a very simple one, if I take a sample of 100 people and I randomize, like I do a 50-50 random split, so half of them go into group A and half of them go into group B, you should expect that on average, the mean height in both groups is the same, the mean weight in both groups is going to be the same, the mean propensity for disease is going to be the same, the mean blood sugar level is going to be the same, the mean BMI is going to be the same. All of these things should be happening if you have randomized correctly. And so if you were to run a randomization strategy and you find that it turns out that, oh, in one group, people tend to be taller, or in the other group, people tend to be a little bit more overweight, something like that tells you that the randomization has failed. And now if you were to use this failed randomization to try to test a drug, those estimates of the effectiveness of the drug, the causal effect of the drug, that treatment effect is no longer reliable. You cannot trust it because you know that the randomization algorithm was flawed. And so testing assumptions is very, very important. The second one I want to touch on is falsification and placebo tests. So what that means, coming back to this malaria setting, is if I was to have two groups of people and neither of them has received a drug, I should expect that those two groups of people will behave exactly the same way in terms of their recovery rates from the drug and from malaria, for example, and in terms of their propensity to get malaria in the future. So coming back to my example of the marketing campaign as a second thing here, if I was to run my model through a case where there was no marketing campaign, suppose I pretend that there was a marketing campaign for half of my customers and the other half did not see it, but this is entirely pretended, so it's not a real marketing campaign. If I run my model, I should find zero effect because there was no real marketing campaign, so obviously there should not be any actual effect. If my model is telling me that there is still an effect, it means that the model is probably not doing a good job. Something is going wrong with the model, and so now that is not reliable. So falsification placebo tests of this kind can also be pretty useful. Irrelevant or confounding features. So what I mean over here is if I know that the marketing campaign is very effective, adding random other things which are not supposed to be effective should not make any difference. So if I train my model using a certain set of inputs, and then I have also the important treatment variable of was the person exposed to the marketing campaign or not. If I start adding random other features such as what was the sunshine on that day, or how much rainfall did they receive last month, things like that should not really make a difference. If I find that my model is very, very sensitive to the inclusion or exclusion of specific features, that is again a signal the model is not good. Out of sample validation is very similar to the machine learning idea of out of sample validation. So if you train on a particular group of customers or a particular set of patients, if you were to rerun your model outside of that group on a new set, the predictions should be reliable even in that set. So your causal effect measurement should not be very sensitive to which sample is actually going in there. And so these out of sample validations can kind of help you understand, is the model stable and is it doing a good job? Multiple causal model. So what I mean here is that sometimes you have the flexibility to run many different methods. So maybe you run a randomized control trial, but you also have an observational model. You can think about how different the two of them are. So if you have multiple causal models and they're all giving you very, very similar effects, very, very similar estimates of what the causal effect is, that again strengthens your confidence that this is in fact correct. And so now you can more confidently go ahead with the assumption that the causal effect is being measured correctly. I gave the example of experimentation in multiple causal models, but generally a correctly run experiment, a randomized control trial, or an A/B test, provided you have randomized correctly and you have thought very carefully about how you are running your experiment, that is the most reliable. Like you can mathematically prove that the causal effect that is recovered from a properly designed experiment is going to be the true causal effect. It's going to be asymptotically converging to the true causal effect. And so that's what people will usually try to do. And so sometimes you have experimental evidence, and you can also train a model. So if you train a model that does a very, very good job of matching the experiment in terms of its predictions, then that should strengthen your confidence in the model as being reliable. And the last one is synthetic data. So what I mean by this is if you construct your own data, so suppose I create synthetic customer behavior data, and I have and I also create marketing campaign data, and the causal effect here, because I'm creating it synthetically, I am kind of assigning a value of 10% to the marketing campaign. Now, when I train my model on this synthetic data, I should be able to recover the true 10% effect. So by construction, I know the effect is supposed to be 10%. And a good model that does a good job of causal inference should be able to recover that 10%. If my synthetic data is constructed using a 10% expected impact, but the actual model is predicting a 20% impact, that means that the model is probably not doing a good job. So synthetic data and kind of like training models on synthetic data can sometimes also be quite helpful as a tool. I think I'll stop here. I think there's about 10-ish minutes left. Yeah, thank you very much. And I'm happy to take any questions if anyone has any.
Thank you, Professor, for sharing your valuable time and for joining the webinar. On the behalf of Organizing Committee, IASTM Conference and iRUJ webinars, I would like to thank all our sponsors and coordinators. I would also like to thank our president. We're happy to hear your comments and compliments or suggestions at our Facebook and Twitter page. This video will be available shortly in our YouTube channel. Kindly subscribe our official YouTube channel, iRUJ Conferences and Seminars, for all past and upcoming webinars and expert lectures. Thank you all. See you on another webinar soon. Thank you, Professor, for sharing your valuable time and joining the webinar.